How do we sever the umbilical cord to our home planet? For billions of years, Earth has provided an invisible, flawless life support system, recycling every breath we take and every drop of water we drink. But as we look toward the rusted plains of Mars or the shadowed craters of the Moon, we face a brutal reality. Space is utterly indifferent to human biology. To survive the cosmic void, we must learn to bottle the biosphere. The mathematics of human survival are unforgiving. A single astronaut requires roughly 30 kilograms of water, oxygen, and food every single day. Multiply that by a crew of 6 over a multi-year journey to a distant Mars colony, and the mass becomes staggering. Launching thousands of tons of consumables out of Earth's gravity, well, is economically and physically impossible. With current propulsion, we cannot pack everything we need. We must regenerate it. This is the domain of closed-loop life support, an intricate dance of physics, chemistry, and biology designed to mimic Earth's ecological cycles within a sealed pressure vessel. In an open-loop system, resources are consumed and waste is discarded. A closed-loop architecture, however, treats waste not as garbage, but as a critical resource. Every exhalation, every drop of sweat, and every biological byproduct must be captured, purified, and returned to the crew. Our proving ground for this technology orbits 400 kilometers above our heads. According to data from NASA, the International Space Station utilizes an environmental control and life support system, or ECLSS. This marvel of modern engineering currently handles the recycling of about 98% of the crew's water and a significant portion of their oxygen. It is a mechanical oasis, proving that we can artificially sustain human life in the most hostile environment imaginable. The ECLSS relies heavily on physicochemical systems. Dehumidifiers pull moisture from the cabin air, while a complex distillation assembly purifies urine into pristine drinking water for air revitalization. The Sabatier reaction combines captured carbon dioxide with waste hydrogen from oxygen generation, producing water and methane. The water is fed back into the system, and the methane is vented into space. It is a highly efficient machine, but it is not a perfect loop. That slight imperfection represents a massive hurdle for deep space exploration. The fractional amount of water lost, the vented methane, and the constant need for resupplied food mean our current orbital outpost is only partially closed. Over a 3-year Martian expedition, those tiny fractional losses compound into catastrophic deficits. Physicochemical machines alone cannot bridge the gap to true self-sufficiency. They lack the elegant, self-repairing complexity of a living ecosystem. Those mechanical limitations force a profound shift in how we design off-world habitats. To achieve true independence, our architecture must evolve from mechanical submarines into living, breathing organisms. We must integrate biology into the machinery. This transition from purely mechanical recycling to organic regeneration is the key to unlocking the solar system, transforming cold metal outposts into vibrant, self-sustaining settlements capable of enduring indefinitely. Integrating life into the loop introduces immense biological complexities. Plants and microbes do not behave with the predictable certainty of a carbon dioxide scrubber. They get sick, they mutate, and they react unpredictably to radiation and microgravity. Designing a system where humans, plants, and microorganisms exist in perfect symbiotic balance requires a level of ecological engineering we are only just beginning to understand. The margins for error are microscopic. Engineers propose solving this through bioregenerative systems, integrating living organisms directly into the life support architecture. Experimental facilities like the European Space Agency's Melissa project and Russia's historic BIOS 3 have demonstrated the potential of this approach. These systems use light, microbes, and higher plants to process waste, scrub the air, and grow food simultaneously. They are miniature engineered ecosystems designed to replicate the intricate carbon and nitrogen cycles of our home planet. At the microscopic foundation of these systems are algae and cyanobacteria, cultivated in glowing liquid-filled bioreactors. These single-celled powerhouses are incredibly efficient at photosynthesis. They consume the carbon dioxide exhaled by astronauts and rapidly produce oxygen and edible biomass. Because they grow in a fluid suspension, they are highly adaptable to the zero-gravity environments of transit spacecraft, providing a dense, continuous yield of life-sustaining resources without the need for soil. But when we reach a planetary surface, the scale of agriculture must expand. Cultivating crops on another world means confronting alien geology. Martian dirt, known as regolith, is fundamentally different from terrestrial soil. It is devoid of organic matter and laced with toxic perchlorates. Before it can support a greenhouse, this regolith must be chemically washed and heavily enriched with recycled organic waste, transforming dead alien rock into a living, fertile medium. Managing that fertilization process is a delicate chemical balancing act. If the microbial breakdown of human waste produces ammonia too quickly, it can poison the crops. If the plants consume carbon dioxide slower than the crew produces it, the atmosphere becomes toxic. Every biological transaction must be meticulously monitored. The habitat becomes a tightly wound clockwork of biological exchanges, where a failure in one component threatens the entire crew. To bypass the unpredictable nature of regolith, future habitats will likely rely on advanced hydroponics and aeroponics. By suspending plant roots in nutrient-rich water or misting them with precise chemical cocktails, we can maximize crop yields while minimizing space and water usage. These controlled environment agriculture systems allow engineers to dial in the exact spectrum of light, humidity, and nutrient concentration, optimizing the growth of wheat, potatoes, and leafy greens for human consumption. Beyond the raw caloric output, these off-world gardens serve a profound psychological purpose. In the sterile mechanical confines of a deep space vessel or a subterranean Martian bunker, the presence of living green plants offers a vital tether to Earth. The act of tending to a garden, of smelling damp earth and watching a seed sprout, provides immeasurable mental health benefits to crews isolated millions of miles from the natural world. Yet every calorie consumed by the crew eventually becomes waste, and that waste must re-enter the cycle. Advanced bioregenerative models utilize anaerobic digesters to break down solid waste, extracting valuable carbon and nitrogen. This process not only neutralizes dangerous pathogens, but also generates methane gas, which can be harvested for rocket propellant or supplementary power. In a truly closed-loop habitat, there is no exhaust pipe, only the next phase of the cycle. The inherent fragility of these artificial ecosystems is a constant shadow over mission planners. Earth's biosphere is massive, capable of absorbing massive shocks and buffering climatic changes. A Martian habitat, however, contains a highly constrained volume of air and water. A sudden fungal infection in the crop bay or a mechanical failure in a water pump can cause the entire ecological balance to collapse in a matter of hours. To guard against collapse, these systems require unprecedented levels of automation. Thousands of embedded sensors must continuously monitor trace gases, water purity, and microbial health. Artificial intelligence algorithms will act as the digital stewards of the biosphere, predicting chemical imbalances before they occur and adjusting lighting, temperature, and nutrient flows in real time. The habitat itself must become a conscious machine, fiercely protecting the delicate biological equilibrium within its walls. Protecting that equilibrium also means defending it from the hostility of the cosmos. The walls of the habitat must be formidable pressure vessels, holding back the vacuum of space while blocking lethal streams of cosmic radiation. Solar flares and galactic cosmic rays can easily sterilize a bioreactor or induce catastrophic mutations in crop yields. The engineering depth required to shield these delicate biological cycles is as critical as the systems themselves. Even with perfect recycling and impenetrable shielding, some microscopic losses are inevitable. Air escapes through airlocks, and water molecules cling to the suits of returning astronauts. To sustain a colony over decades, we must master in situ resource utilization. We will need to mine subsurface Martian ice to replenish our water reserves and extract carbon dioxide from the thin Martian atmosphere, feeding these local resources into our architecture to make up for the inevitable deficits. As we scale these systems from small exploratory outposts to sprawling settlements, the engineering paradigms will shift again. A full-scale Mars colony might feature massive pressurized biodomes, housing complex multi-tiered ecosystems with insects for pollination and perhaps even small aquatic life for aquaponics. The echoes of those initial theoretical hurdles will persist, but the solutions will grow exponentially more complex, blurring the line between machine and nature. This mastery of life support is the absolute prerequisite for humanity's cosmic expansion. It is the invisible foundation upon which all our interplanetary ambitions rest. Without it, our rockets are just temporary excursions. By learning to engineer ecosystems from scratch, we are not just solving a logistical problem, we are taking the first agonizing steps toward becoming a truly multi-planetary species, capable of taking the spark of life wherever we go. Ultimately, this endeavor forces us to deeply understand the very nature of our own existence. Earth itself is a closed-loop system, a singular massive spaceship hurtling through the void powered by a fusion reactor 93 million miles away. By attempting to replicate its intricate biological ballets in miniature, we gain a profound appreciation for the fragile, interconnected web of life that has sustained us for millennia. The engineering of closed-loop life support for off-world habitats is arguably the most complex challenge in modern science. It requires us to seamlessly weave together thermodynamics, microbiology, and aerospace engineering. As we perfect these technologies, we do more than just guarantee our survival on the desolate plains of Mars or the dusty shores of the Moon. We ensure that humanity and the vibrant biology we carry with us can flourish among the stars forever.